All right, physics, this is Horner, and today we're going to look at 2001 B1, an old AP Physics B question. This question's really good because we have a device similar to what we used in the lab, but instead of swirling it around our head, we're actually swirling it up and down. So here we're standing, we're holding on to this, we're smiling because we love physics, and this thing is swinging up and down. When you swing it up and down, it's a lot different than when you swing it above your head. When you swing it above your head, there's always a force of tension pointing towards the middle. In this one, it's a little different. The force of tension is the greatest when it's pointing down, and it is the least when it's pointing up. In fact, the force of tension essentially disappears, and the only force acting on the ball is the force due to gravity. So let's look at that in a free body diagram. On the figure below, so we look at these two, they want us to draw and label all the forces exerted on the ball when it's at points P and Q. So here's P and here's Q. Remember, we're twirling it in a vertical circle. So the first force we always have done on these is the mg force, or the force due to gravity. We'll do the same thing at point Q, and we've got mg. We also have a tension force at both of these. So the tension force is pulling towards the center for each one. So for this one, it's horizontal, and for this one, it's vertical. As long as you just put those forces, you would get all 4 points. If you tried to put anything else, you wouldn't. One note that I need to tell you about is they will not accept FC instead of T. You really need to call it T. So remember, we said that the centripetal force, quote unquote, is usually either a tension or a normal force. Here it's a tension. It was a normal force when we had the rotor. So remember, the rotor is the great big wheel that you stand inside of, and it spins really fast, and it pins you against the wall. It's really pulling you in so that you don't go flying on the outside. So this is 4 points altogether, one for each one of them correctly labeled. Make sure that the ends are always touching the dot, and make sure that you have an arrow pointing away from the dots. That's extremely important in order to get your 4 points. For the next part of this problem, they want us in letter B to derive an expression for V min, the minimum speed of the ball can have at point Z. Well, if we go back to the very beginning, you'll notice that point Z is at the very top, and there's something important here that we have to recognize. There is no tension pulling that ball down. Instead, the only thing that you have bringing the ball down at point Z is only mg. So if we did a free body diagram at point Z, the only thing you would draw is just mg. The string's still connected, but there's no tension in the string. The string is just there. And some people struggle with that a little bit, but if you think about it, you'll notice that it really makes sense. If you were to stop swinging it and it stopped here, it would fall straight down. If you stop swinging it at the bottom, it would just sit there because there is tension pulling it up. Here, tension doesn't really pull it down. It is the force due to gravity at the very top that pulls it down. If we went over here, then we'd have a little bit of tension, a little bit more, but mg actually helps the tension in this case. So because of that, we're going to say the sum of the forces at point Z are equal to mass times acceleration. So we know it's accelerating. And at this point, it's accelerating because of the force due to gravity. Because of that, we're going to say mg now is equal to, mg, is equal to ma. And this a, remember, is the acceleration due to the centripetal force. And so AC is equal to v squared over r. Now we need to substitute in what we have for v squared over r. So we're going to say mg is equal to mv squared over r. You'll notice that both of the masses actually cancel out here. And if you solve for the minimum speed to have the ball at the top, okay, so that's why there's no tension on this one, is because the ball at the top, we are looking for the slowest speed it can have at the top, which means that we don't have any tension at the top. That v then is equal to g times r, and we have to take the square root. So all we did is we solved this again. Now we have to be really careful, because if we go back up and look, it says we need to express all of our answers using just some certain letters. Express all algebraic answers in terms of given quantities. Notice that, and this is picky, I know, the R here is not a lowercase. They're using a capital R in this problem for the radius of the string out to the ball. So we really need to make this a capital R. I would go ahead and do that for each one of them. That way you won't lose a point because they were being too picky. Anyway, that is the answer for letter B. It is the speed, minimum speed, so you might even write MIN here, is equal to the square root of gravity times the radius of the circle. Notice mass doesn't take any part in this. That is letter B. Let's go ahead and take a look at letter C. For letter C, we're looking at a different point. Now they want us to find an equation for the maximum tension the string can have without breaking. So that's Tmax, and that's what they give us. They want us to derive an expression for the maximum speed the ball can have at point Q without breaking the string. So let's just review again where point Q is. If you go back up to your original problem, point Q is at the very bottom. So we need to go ahead and do a free body diagram for what's going on at the very bottom. At the very bottom, we have, if we have our hand right here, and so, well, let's go back. Let's say here's our circle, okay? We have the ball at the bottom. We have our hand right here. The hand is connected to the vertical string. We know that pointing straight down, and let's actually do this in a different color. We know pointing straight down from the ball is mg, and we know pointing straight up then would have to be the tension coming from the ball up to where your hand is. So that's the tension on the ball. At this point, we know the sum of the forces would have to be equal to MAC. Because this thing is turning in a circle, we have a centripetal acceleration. The force going up is tension, so we're going to put tension minus, and then the bottom force is mg, and that's equal to mass times the centripetal acceleration because it's going in a circle. Now we can go ahead and substitute in for AC the equation that we've been using. So AC is equal to V squared all over R. And notice we are using a capital R here. So now this equation becomes T minus mg is equal to m times V squared all over R. We need to now solve for V. So let's go through and let's do that. We're going to multiply both sides of this equation by R over M. So we're going to multiply both sides by R over M. If we do that, we get R over M times the maximum tension minus mg, and that's equal to V squared. And now we need to take the square root of both sides. So now we have V is equal to the square root of R over M. Make sure both things are under the square root. Don't try to put the M down here. They'll count it wrong. And then we have the maximum tension minus capital MG. And so what we did here is we're trying to find out what is the maximum speed that this ball can go without breaking the string. So we call this the maximum tension. The tension and the weight here have to be equal and opposite, so we've got that. We know that it's accelerating. It's got a maximum acceleration, so we can say that this is the maximum tension. We then went through and used AC is equal to V squared over R. We have mv squared over R. We multiplied both sides by R over M to get the M and the R on the other side. Once we did that, we ended up with this equation and then just took the square root, actually switched the sides too because I like to have the unknown on the left and all the numbers that I'm going to put in on the right. Now, because this one doesn't have any numbers in it, they are relying on you to be able to solve actually for V here. That's actually one of the points. If you had this equation, they would give you a point, but then there's another point for actually rearranging it and solving for V. Okay, so for letter D, this is actually the very last part. So what we just got done doing here was letter C. I just went a little bit too far. So this is letter C. Letter D is the very last part, and they want us to describe the motion of the ball immediately after the string breaks. So if it's at point P, let's go back up and look one more time at what point P is. So point P is on the very left side. So let's go ahead and draw the circle and draw point P. So here's the circle, here's point P. If the string broke, okay, so it breaks right there, and the ball's moving in this direction, we know that it would fly off tangentially. It would go straight up. So you'd actually need to write straight up tangent. So tangent, sorry about that, to the circle or the circular path, either way you do it. That's one point. The other point is think about the ball. If it's going straight up and it's just left the circle, it will also be slowing down. So the ball will go up, but it should be slowing down. That's the second point. Lots of people miss that point. They get this, but it's described the motion of the ball, so we know the direction, and we also know that it is slowing down. The speed is getting smaller and smaller. That is basically this problem, pretty easy to do. Not too much to it. Probably the hardest part of the problem is letter C, where you have to do a little bit more of the algebra. But other than that, that's it, and you should be good.